In examples of metric space part 1, I explained some example on metric space. Now in this example of metric space part 2, I extend some more examples on metric space. So consider the example. The first example is the set C of closed interval 0 to 1 means set of continuous function on closed interval 0 to 1 with metric D defined by D of fg is equal to supremum of absolute value of f of x minus g of x belongs to the closed interval 0 to 1 for all fg belongs to set of continuous function on closed interval 0 to 1. Now we have to prove that this D is a metric on the set of continuous function on closed interval 0 to 1. So solution, consider D of fg. By definition of D of fg, this is a supremum of set of all absolute value of f of x minus g of x says that x belongs to the closed interval 0 to 1. Now this absolute value of f of x minus g of x is always a positive and we take the supremum of that. So therefore this must be the greater than or equal to 0 and then therefore d of fg is greater than or equal to 0. Now next, that is the consider d of fg is equal to 0. Now substitute the value of d of fg is a supremum of set of all absolute value of f of x minus g of x such that x belongs to the closed interval 0 to 1. We have to consider equal to 0 is here. Now as supremum of absolute value is equal to 0, absolute value of f of x minus g of x must be 0 for all x belongs to closed interval 0 to 1, and this is nothing but the f of x minus g of x is equal to 0, and therefore f of x is equal to g of x, and therefore f equal to g, and therefore it satisfies the coincidence, means d of fg is equal to 0. We get implies and implies by f equal to g. Now next, symmetry. Consider d of fg. Now by definition of d of fg, it is nothing but the supremum of set of all absolute value of f of x minus g of x says that x belongs to the closed interval 0 to 1. Now by property of absolute value, in place of f of x minus g of x, take here absolute value of g of x minus f of x. Value is not changed then. So but here supremum of absolute value of g of x minus f of x such that x belongs to the closed interval 0 to 1 is nothing but the d of gf, and therefore we get the d of fg is equal to d of gf, and therefore it satisfies the symmetry. Now next, consider d of fg is equal to, by definition of d of fg, this is supremum of set of all absolute value of f of x minus g of x such that x belongs to the closed interval 0 to 1. Now here add and subtract h of x, and then by property of absolute value, this must be the greater than or equal to supremum of absolute value of f of x minus h of x plus absolute value of h of x minus g of x such that x belongs to the closed interval 0 to 1. Now split this, we have get this is greater than equal to supremum of set of all absolute value of f of x minus h of x such that x belongs to the closed interval 0 to 1 plus supremum of set of all absolute value of h of x minus g of x such that x belongs to the closed interval 0 to 1. Now by definition of d, this is nothing but the d of fh, and by definition of d, this is nothing but the d of hg, and therefore it satisfies the triangle inequality. Next, Cosqueeze inequality. This inequality is important for further solving the problems. What that say inequality? That is for p is greater than 1 and finite, we denote LP the space of all sequences xi such that summation of absolute value of xi raised to p I is equal to 1 to infinity is finite for any x is equal to sequence xi and y is equal to sequence yi belongs to LP, then this satisfies this inequality is called as a Cosqueeze inequality. Now the example, the set r raised to n. R raised to n means all order n tuples with function d defined by d of xy is equal to summation of xi minus yi bracket square I is equal to 1 to n raised to 1 half for all n tuple x1, x2, xn and y equal to order n tuple y1, y2 up to yn is we have to proving this D is a metric. So solution, consider any three element x, y, z belongs to the r raised to n. Then consider D of xy. By definition of D of xy, this is substitute the value. Now here this square value is always positive and we have to taking the summation of this square value, so it must be the positive and under root of positive is again positive, so the whole term is positive and this is nothing but the d of xy and therefore this must be the greater than or equal to 0 and therefore it satisfies the non-negativity. Now next consider d of xy is equal to 0. Substitute the value of d of xy is summation of xn minus yn bracket square n is equal to 1 to infinity raised to 1 half is equal to 0. Now here we have to square both the sides. So we get this term. Now the summation of square term is equal to 0 and therefore each square term must be equal to 0. From that we get x1 minus y1 equal to 0, x2 minus y2 equal to 0 and it implies by x1 is equal to y1, x2 is equal to y2 and it implies by we get the sequence xn is equal to sequence yn and therefore we get the x is equal to y and hence it satisfies the property coincidence. Now symmetry. Consider d of xy. Now by definition of d of xy, we get after putting the value we get this value and here xn minus yn bracket square in place putting the yn minus xn square because the both are the square, so we get the same value here. Now but this is nothing but the by definition of d of yx and therefore it satisfies the symmetry. Now next triangle inequality. Consider d of xy. This is equal to summation of xn minus yn bracket square n is equal to 1 to infinity raised to 1 half by definition of d of xy. Now here add and subtract zn. Now xn minus zn put as an and zn minus yn as a bn. We get this value. Now apply the Cosqueeze inequality. We get this value is greater than or equal to summation of an square n is equal to 1 to infinity raised to 1 half plus summation of bn square n is equal to 1 to infinity raised to 1 half. Now by back substitution means putting the value of an and bn, we get this, but this is nothing but the d of xz and this is a d of zy and therefore d satisfy this property d of xy is less than equal to d of xz plus d of zy and therefore it satisfies the triangle inequality. Therefore d satisfy all that four properties, that is the coincidence, symmetric, triangle equality and non-negativity. Therefore d is a metric and therefore R raised to nd is a metric space. Now this metric space is called as a Euclidean n space or n-dimensional Euclidean space. Next example, show that the set R raised to n means same as to define in the above example, that is the n ordered tuple with d dash defined by d dash of xy is equal to summation of absolute value of xi minus yi, I is equal to 1 to n. For all x is equal to order n tuple x1, x2, xn, y equal to order n tuple y1, y2, yn belongs to R raised to n is a metric space. So for that we have to consider one by one properties. So first property, that is the non-negativity. So consider any two element belongs to R raised to n. So d dash xy, by definition of d dash xy, we get summation of absolute value of xi minus yi, I is equal to 1 to n. Now this absolute value is always a positive and its sum is therefore positive. So therefore this must be the greater than or equal to 0. So d dash of xy, we get the greater than or equal to 0. Therefore it satisfies the non-negativity. Now next, consider d dash xy is equal to 0. We have to bring the coincidence, means now we have to bring the x is equal to y. So by definition of d dash xy, we get value of d dash xy is summation of absolute value of xi minus yi, I is equal to 1 to n equal to 0. Now summation of absolute value is equal to 0 and therefore each absolute value must be equal to 0. From that we get the xi minus yi equal to 0 and it gives the xi is equal to yi for all I, and therefore x is equal to y, and hence it satisfies the coincidence. Now symmetry, consider d dash xy. So by definition of d dash xy, putting the value of d dash xy here, and in place of absolute value of xi minus yi, by property of absolute value take absolute value of yi minus xi, so that the value of this is not changed, so that equal to d dash of yx by definition of d dash, and therefore we get the d dash xy equal to d dash yx, and therefore d satisfy the symmetry. Now next, triangle inequality. So consider d dash xy. So by definition of d dash xy, we get this value is summation of absolute value of xi minus yi, I is equal to 1 to n. Now here we have to add and subtract zi, and then by the property of absolute value, this is greater than or equal to summation of absolute value of xi minus zi, I is equal to 1 to n plus summation of absolute value of zi minus yi, I is equal to 1 to n. Now value of this is nothing but the d dash xz, and value of this is d dash zy by definition of d dash, and therefore d dash satisfy the triangle inequality. So d dash satisfy all the four properties, and therefore d dash is a metric, and therefore R raised to n d dash is a metric space. Now this metric space is known as a rectangular metric. Now on the next lecture we have to get some more examples by the title Example of Metric Space Part 3.